Swayam Prabha. Digital India. Educated India.
Good morning, everyone, and welcome to this class on Introduction to Aerodynamics. In our last lecture, we went over the differential form of the governing equation with respect to so we saw the continuity equation based on the conservation of mass, and then we looked at the momentum equation. I said that in the momentum equation, setting up of the free body diagram, so essentially we took a differential element of fluid. We said that this one was a Lagrangian element. Essentially, we are looking at a dx dy dz. So it is a mass that is described by, contained in that geometry defined by dx dy dz extents. And this mass, of course, at time t is equal to 0, it is by our choice that it has a nice, regular geometric shape, but it moves through the fluid. And what we said was, in as much as we find the acceleration of a substance subjected to force, it is similar to the acceleration of Lagrangian element of fixed mass identity. At time t is equal to 0, it has dx dy dz, nice and regular shape. But again, as this Lagrangian element moves through the flow field, it will, undergo deformations and stretching, straining, etc. But nonetheless, its mass will remain constant. And then, if we can find the forces acting on this chunk or this, small parcel of differential element of fixed mass identity, if we can find the forces acting on them. So if you remember in high school physics or even before that, you might have started doing the free body diagram. So in this case, we did the free body diagram and essentially equated force to the product of mass of that infinitesimal element multiplied by the material derivative of velocity. Okay, because here we are looking at the acceleration of the elementary chunk or the infinitesimal chunk of fluid as it is moving through the flow domain. And if you remember, from our initial lectures, that the material derivative is nothing but you measure velocity at location 1 at time 1, then you let some time elapse, the parcel moves to a new location, it has a new location, new velocity. So all you do is you measure the difference of velocity at those two locations, add those two timestamps and divide it by delta t. And that is essentially how we measure, acceleration even for objects. If you think of like a, vehicle moving on on the road, or a soccer ball that has been kicked by a player, or a cricket ball that is crossing the boundary, essentially the forces acting on the ball and the acceleration, so the Lagrangian acceleration. So here also, since we are following a fluid element of fixed mass identity, we can use that same kind of a sense of things. And setting up the free body diagram is actually what is the tricky part. Now I will go back to the presentation mode so that you can see the the slides of interest. So these you have already seen. So I will quickly go over them. You can see that there's a lot of repetition that I am doing in this portion, because these are the things that will be very useful in the long run, because the Navier-Stokes equation will be part and parcel of your aerodynamics, your association with aerodynamics. And as I said, this differential form is primarily useful. Of course, it is useful for understanding the nature of things, but it is also useful in the computational fluid dynamics approach of solving problems, because we will see that these equations that result from what we are doing right now, they are complicated equations. In fact, you will hear the word that they are non-linear equations, they're coupled equations, they don't have any analytical solutions. You will hear all these things. So what happens is eventually we seek numerical solutions. So you have a computer that can crunch numbers, and these partial differential equations can be converted into difference equations, and computers are very good at solving these differences. how do you form the difference equations is something that is part and parcel of CFD. Okay, so we will touch upon that because this is an introductory course. It is important that you have a flavor of things, but of course, we will not get into the rigorous, the in-depth aspects of CFD, because CFD is a course in itself. In fact, it might even comprise of several courses at undergrad and grad levels. But nonetheless, you might wonder why we are doing all these, complicated differential equations. One of the, many answers is, as you have seen, if you non-dimensionalize them, you get those physical parameters, the non-dimensional parameters like Reynolds number, Mach number, Prandtl number, which tell you of the dynamic similarity between problems. Remember, these things are known as similarity parameters. So these governing equations in differential form, when we non-dimensionalize them, these non-dimensional groups fall out in front as coefficients, and it can be shown that they act as similarity parameters and create dynamic similarity between problems when the similarity parameters are the same and the geometry are okay. So the flow is over similar geometrical shapes. Secondly, another big use of these differential forms is in the computational way of solving these problems, and we will see these things later. Now let us get back to, so in the last lecture we actually went over this slide. So we said that this one, remember, so essentially this is nothing but the F is equal to ma formulation, and this is, this thing from your study of Newtonian mechanics. If you know what is the force, or rather if you know, any two of these things, you can find the third variable. So in this particular case, remember that our fluid volume, we are looking at the Lagrangian form. So this is almost like a, vehicle or a moving object that. So if you can find its acceleration, so as you understand, the acceleration is given by then the material derivative of the. Now why I'm writing small u? It is because I'm looking at the u component or the x component, sorry. So in the vector sense, you can still write f vector is equal to m times a vector, which is the material derivative of the overall vector, overall velocity. You can, write this thing, but then, your mass would be rho times dx dy dz, and your acceleration will be this, and that will be the net force. Okay, so the vector force acting, which is the net of all the forces acting on this elementary chunk of fluid. And this is comprised of those body forces, surface forces. Surface forces are comprised of, the normal forces and the shear forces. So all those things are there, but you can also just write it for the x component. So you can say, just focusing on the x component of force, this is equal to rho times. So this is not p, okay, this is rho. And again, since it's an infinitesimal element, we can think that rho is constant in this region. And then you say du dt. So in case you are just looking at the x component, so this one is, if you are looking at just the x component, then you can write something like that. So this one is focusing on the x component of the above. Okay, so anyway, so as you can now see, last time I emphasized that the normal forces, see, it's not just P. Okay, so P times the cross surface area creates the normal force, but you see that we also have these tau terms with same subscripts. You remember from last lecture that I said that the second subscript tells you the direction of the force. The first subscript tells you the orientation of the plane on which the force is acting. Okay, so you see, I am saying these things many times. You will perhaps appreciate it eventually, that sometimes some of these things become a little confusing. So what I'm saying is, you find the pressure, and then the product of the pressure with the area of this cross section gives you the normal force on this surface. But then you also have this tau xx, which results from the viscous nature of the flow. Typically, we think that viscosity gives rise to these tangential forces. For example, here you have tau yx, which says that this is shear force in the x direction, second subscript, on the plane whose normal is in the y direction. Okay, so you can see that this is a shear force, a tangential force, and this is what we are typically used to understanding when we think of viscosity. We think of something like this, and this essentially, when you rub your hands, one hand tugs the other one along its direction, etc. So we are comfortable with that description or that effect of viscosity. But this tau xx, which is a compressive or expansive force normal to the surface due to viscosity, is a little less appreciated, or sometimes there is some confusion around it. And we will see that these stress elements, tau xy, tau yz, tau xx, and all these things, have a relationship with velocity gradients. In fact, this tau xx is given by lambda time the divergence of the velocity vector plus 2 times mu multiplied by, okay, so this is, so you see that we have viscosity that comes in here, and this is again, this goes by the name of second coefficient of viscosity as well. And you see that the velocity gradient in the x direction is something that is contributing to the generation of this stress. Okay, this is a normal stress. And in shock waves, for example, if you think that you have a flow is going from left to right, and you have a shock wave sitting here, and you are looking at a flow problem on the right hand side, post shock wave. So this is a shock wave here. What happens is, in the shock wave, the velocity of this flow decreases rapidly. So flow here could be at much higher speeds than the flow on this side, because the density increases. Okay, so conservation of mass requires the velocity to reduce after the shock wave. So what happens is there is a very rapid decrement in velocity as the flow is going from the left pre-shock to the post-shock state. In problems like this, your du dx can become significant, and hence your tau xx and terms like that can become important in the problem. In a lot of problems, you can actually ignore tau xx if the velocity gradients in the direction of the flow is not very large. But in specific problems, for example, the problem of the shock, flow through a shock wave. So let me just write it, because you can then look it up. This is a normal shock wave. So as the flow goes through this normal shock wave, its velocity decreases rapidly. So the thickness of the shock wave is in the order of few mean free path of the molecule under the given circumstances. And so this is a very thin region across which velocities change extremely rapidly. So in that shock layer, your velocities are changing. So gradients of velocity in the direction of the flow. So here you can think that your u has some value. Your here u has some other value, and du dx is extremely large. So if you zoom into this shock region, the few mean free path width, your u is changing like hell. So the du dx term is very large, and hence compressive stresses due to viscous effects are dominant inside a shock wave. Okay, so now you understand that the P, thermodynamic pressure driven generated force, is there. Velocity gradient driven forces are there, which is normal to the surface. Then you have the shear or the tangential forces. So here we are looking at all the forces that have some contribution in the x direction. So we are really looking at the x momentum equation, or x force momentum balance equation. And a little bit of a word about why we have these sign directions of these forces. As I said, the convention is, what we think is UVW. Each of them increases along x, y, z directions. Okay, each of them. So it's not just U increases along x or V increases along y like that. U increases along x, So when x increases, u increases. When y increases, u increases. When z increases, u increases. Similarly, x increases, v increases, y increases, v increases. So that kind of increment is there. So each of these components increase with each of these coordinate axes. So what that gives you is, now if you just think of the u, say suppose v and w are constants, then u is changing, and I said u is changing with x, y, and z. So in this case, what is happening? U is increasing with y. So the value of u on the surface A, B, C, D is higher than the value of u on the surface just below A, B, C, D. Okay, because as I said, this u is increasing with y here. So now what will happen is the lower surface will tug the surface ABCD from in its direction because it is a slower layer. So the layer ABCD will be kind of tugged to the left, or the ABCD will be, will experience a shear force in the negative x direction. On the other hand, if you look on the surface EFGH, the layer just above EFGH has a u velocity which is higher than the u for EFGH. So what will happen is that layer sitting just above EFGH and touching it will actually tug this layer EFGH to the right. Okay, so similarly, all these other forces are there, and you by now you know that if you kind of generate or write the values of these forces on these surfaces, like this surface. So surfaces that are adjacent to the origin. Okay, so if this is the origin, then you have this surface AEHD, then surface HDCG, and then surface ADCB. So here we write these values. Okay, so these are the surfaces adjacent to the origin, and then we obtain the values on the opposite faces using that Taylor series expansion. Okay, I will not get into the elaboration of this thing anymore. I think I have repeated this thing many times. If you have watched my videos, the leading videos, then you must have seen this thing several times. So if you use just the pressure terms and not talk about the viscous forces due to viscous effects, then we saw that you get the Euler equations. Okay, so these are the Euler equations. These are, the force, well, the force and product of mass into acceleration when we are not considering your body forces, or we're not considering the viscous forces. Viscous forces meaning forces generated due to viscosity. Now, if body forces were included, then of course, some of these terms would come into the the free body diagram. So you draw the free body diagram, you insert the components of your the effect of body force, and then these equations will fall out. Now, I said in the last lecture that here, when you include viscosity or the effect of viscosity, so because remember, inviscid fluid, in ideal fluids. So ideal fluids are where there's no viscosity, but as the name suggests, it's an ideal assumption. In most cases, viscosity is there, but the gradients of velocity are such that the viscosity doesn't manifest itself in the form of forces, because you already saw that tau xx has something to do with dou u dou x, although I wrote du dx, but you understand the sense of it. So dou u dou x, because if u has variations in other directions, then you write the partial change of u with respect to a certain variable. If u is changing only with x and not with anything else, then dou u dou x, is essentially you can write du dx, because so you write d by dx when you are things are changing with other variables as well. Dou u. So it's a partial differential and a differential. Okay, I think you have some idea about the difference between these two. Now, when we include the forces due to viscosity, you see that we have these extra terms. And of course, here again, we have dropped the body terms, body force term. So if you want to include it, then you can bring these guys back here. Okay, so this is due to pressure, thermodynamic pressure effect. This is due to the viscous force effect. And here you see that we have, tau xx, tau yx, tau zx. So normal stresses are there and tangential stresses are there, or shear stresses are there. And you see that we have in the tau, we have tau xx, tau yx, tau zx, tau xy, tau yy, tau zy, tau xz, tau yz, tau zz. Now there are nine different taus, and now by now you understand that the subscripts kind of tell you which plane and which direction this particular shear or normal stress due to viscosity is acting on. If you bring in the body force terms, then you have to add some of these extra terms. And you understand that this is the most generic expression, at least a relatively generic expression. Okay, so anyway, so this one is from contribution from the body force term. This is contribution from the viscous terms. Viscous nature contributes to these terms, body force. In a lot of aerodynamics problems, we ignore body forces, not very significant compared to the other forces at play. But then again, if you are really being rigorous about it, you have to show before you neglect body forces that body forces, is of an order of magnitude lower than these other forces. The forces due to pressure variation, forces due to shear force and viscous effects. So it depends on the problem. In some cases we will ignore it. In some cases we will use it. So it depends. In fact, even the viscous forces, as I said, can be ignored in some problem, and we just we have this nice easy Eulerian form. Now, last lecture, this is where we pretty much ended. We said that okay, so we have the continuity equation, we have the x and y and the z momentum equations. We will get into the energy equation in a moment, but at this point we saw that there were rho u v w. So one variable, two variable, three, four variables. Then we had pressure, and then we had all these viscous stresses. Okay, shear stresses and normal stresses. Now the thing is, you see, we have only 4 equations, and we have a lot more variables. Thankfully, we will see that your tau xx, tau yx, tau zx, etc. Although we said there are 9 of these, but you will see that there is something that happens by which your tau xy can be written as tau yx, and we will kind of show why this happens. Tau yz, tau zy, this thing happens. So then instead of 1, 2, 3, 4, 5, 6, 7, 8, 9 unknowns, we actually end up having 6 unknowns. So because your tau xy becomes same as tau yx, this thing tau xz becomes same as tau zx, tau yz becomes same as tau zy, etc. Okay, so then if you count, then we have 1, 2, 3, 4, 5, 6. So 6 shear stress terms. Now what happens is you have a lot more unknowns than the number of equations, which is only 4. Okay, see, just the shear force terms, or rather the shear stress terms, because these are the stresses. Stress is like force per unit area. You see, you have like 6 shear stress terms, and we have just 4 equations. So what we do is we invoke these constitutive relationships. Okay, that gives you more equations, so that we can close your system. We will also see that there is this. This is also another constitutive relationship, which essentially is from thermal conductivity in the energy equation. But at this point, we let us focus on these elements. So once again, I think this is something that I wrote in the previous page, that so these are all the shear, and so these are the shear stresses, and these are the normal stresses due to viscosity. And you see that the normal stresses have a form that is quite different from the shear stresses. Okay, so the normal stresses tau xx, so this is shear, sorry, compressive stress or expansive stress, but at least normal stress due to on the x plane. So when I say x plane, it means the plane whose normal is in the x direction, and the force acts along the x direction. So the normal to that surface is along the x direction, and the force in itself acts along the x direction. Okay, so that is tau xx, and that depends on the divergence of the velocity field and the dou u dou x. Okay, so this is the dou thing I was talking about. It's something that comes from partial differential equations. If a variable like u changes with many other independent variables, then what we say is this thing means that we are looking at the change of u with respect to x only, holding everything else constant, something of that sort. So then now you have tau xx, tau yy similarly means the stress on the y plane in the y direction. Okay? And that again has some relationship with dv dy. Similarly, tau z has something to do with this, the rate at which the w component is changing with z. And I just talked about the shock wave being one of the examples. There are other examples as well. On the other hand, here you see that here the subscripts are different, and we will show this thing, why or how or when this thing happens. In most cases, you can assume that you can switch the coefficient, the subscripts, and you can use the equality. How this happens, we will show in the next slide. Essentially, what you do is you take a infinitesimal element of the fluid, and you calculate the moment of these shear forces around, say, the center of mass. It can be shown that the the moment due to the shear forces, if you put them on the left hand side and you equate it with I times alpha, where alpha is omega dot, it can be shown that the product of these shear stresses with, or rather the moment of the due to the shear forces on the left hand side becomes equal to 0, because in the I expression you actually end up having this delta x square plus delta y square, which is so we will have this thing in one of the subsequent slides. So the moment produced by this thing ends up becoming 0, and that's how your tau xy, tau yx becomes same. However, if you have a situation where the moment doesn't become 0, say around the centroid, it doesn't really matter. You can take it around the centroid, you can take it around this by using the parallel axis theorem, etc. But you will see that because your delta x or your dx, because these and these are small numbers, in the expression for the moment of inertia and all this, the moment of inertia product with the alpha becomes 0. So typically you end up with just these shear forces are the same. However, in some circumstances, you can have a situation where the moment due to some other body force is not vanishing. Okay, so then some different situation can happen. But here, so that equivalence is there. So the subscripts can be interchanged, and it can be shown that these shear stresses, say tau xy, is related to mu times dv dx plus du dy. Similarly, this tau yz is related to dw dy plus dv dz, etc. Now let us first look at okay, let's see what we have in the next slide. Okay, so here we have some, okay. So now the thing is, when we talked about, say, so essentially we will focus on some of these discussions that why or how these things happen. Because I think when we discussed we talked about the drag problem. We started this semester with talking about drag on aircraft, wings and fuselage, etc. And we talked about, the wall shear stress. So if you remember, we said wall shear stress is equal to mu times du d, say, eta, where eta is the wall normal direction and u is the velocity parallel to the wall. Okay, so do not think of it as UVW. You can think of it if your x-axis is along the wall at that point. So then we said that the shear stress at the wall is equal to mu times the gradient of velocity normal to the wall evaluated at the wall. So this is the form of shear stress that we had introduced. Now you have to keep in mind that this form is valid for a flow problem. Say in that kind of problem, we said, okay, you have a surface of the wing. Your flow is going from, say, left to right. And then you take a wall normal direction. You have the boundary layer eventually asymptotically becoming free stream velocity. And again, I must emphasize that this thickness of the boundary layer, of course, it depends on the problem of hand, but in most practical cases, it would be of the dimension of, say, millimeters. Of course, in hypersonic flow problems, you have very large boundary, thick boundary layers. Also, as you move along the boundary layer, its thickness will increase. Then, depending on whether you're looking at a laminar or transitional or turbulent boundary layer, again the nature of increase of thickness with Mach number and extent, etc., will change. But nonetheless, what I'm trying to say is, here you see we have some. So this is a case which we will call parallel flow problem. Okay, so here you don't have a variation in the v component of velocity or w component of velocity. Now, when you study boundary layer theory, you will see that the wall normal direction velocity variation is tremendous. It goes from zero on the wall to all the way to free stream within a small extent. Okay, so the gradient of velocity is very large. So the gradient of the u component of velocity is very large. And so in the calculation of shear stress, we look at that variation only. Now V component is not zero inside the boundary layer, but it's really negligible. W component really doesn't come into W component is there, but if you are talking about a 2D problem or to flow over a wing and you take the cross section, the W component, we often ignore. Of course, it depends on the problem. It depends on the way you align your coordinate system as well. But long story short, in this case, we are looking at a parallel flow problem. Okay, so your streamlines are oriented parallel to the surface, and the gradient of velocity is primarily in the wall normal direction. So for that class of problems, the parallel flow problems, you can say, the shear stress is given by a product of this, shear stress for Newtonian fluids is given by a product of this coefficient of viscosity and the gradient of velocity in the wall normal direction. However, these are the more generic forms. Okay, so this thing is really a combination of the coefficient of viscosity multiplied by the summation of these two velocity gradients. On the other hand, for parallel flow, where you don't have a gradient in the other components of velocity, or you don't have significant gradients in the other component of velocity, sometimes you see a form like this. So although you see a form like this, you have to keep in mind that the generic forms are actually this. And where do we get these generic forms? Now, the derivation of these generic forms is, I would say, beyond the scope of this introductory course. Essentially, it involves some fourth order tensor considerations. You will hear something about the traction vector, the wall normal vector, and then there is a the stress tensor of order 2, second order tensor, can connect the traction vector with the wall normal vector. Similarly, your a fourth order tensor will connect your the stress tensor with the strain rate tensor, etc. And from there, with the extra assumptions of Newtonian fluid, isotropic behavior, homogeneous behavior, etc., you can eventually show that these constitutive relationships hold. Okay, so we will not get into those, but at least we can talk about what is homogeneous. Homogeneous would be when, say, a property such as mu does not vary from location to location. Okay, homogeneous. Just check the spelling. Nowadays we have spell checks, so sometimes we are less used to remembering the right spelling of some of these things. So homogeneous means the properties are not changing with location. Of course, U, V, W, these are changing, but when we are saying homogeneous, these are the properties of the fluid, and say viscosity is one of them, and we are saying that this viscosity is constant, in the region that you are looking at. And isotropic, so remember in the derivation of this fourth order tensor algebra is involved with the assumptions of Newtonian fluid, that isotropic behaving fluid. Isotropic behavior means the properties are same when evaluated in different directions. For example, you might think of, say, refractive index of a fluid. In this case, refractive index is not relevant, but in different directions you have the same refractive index. So you can say it's isotropic with respect to refractive index. Homogeneous and Newtonian is. We will come to that part of the discussion, but at this point, let me let me at least say that Newtonian fluid is where, for a fluid where the stress is proportional to this, linearly proportional to the rate of strain, and we will show you what that is. Okay, so Newtonian fluid, if you look at this particular diagram, so I'm moving back and forth between the slides a bit. Sometimes keeping it linear is a little difficult. So you see, if you plot the shear stress versus the strain rate. So now, why are we plotting shear stress with respect to strain rate? It's a question that can come to some of your minds, because for people who remember their lessons from solid mechanics, you remember that we have generally we say stress is proportional to strain. Of course, it can be linearly proportional, or it can have something which is not linear, but stress was proportional to strain for solids or elastic solids. So essentially, you apply a stress. Stress is nothing but force per unit area. So if you apply a stress which creates a strain in the solid deforms and it resists the stress that is causing it, and then we can calculate that what stress is causing what strain. Okay, well, what stress is causing what deformation, and from deformation divided by initial dimensions, you can find what strain. So stress strain relationship in solids. In case of a liquid or fluid, it can be a gas as well, gas or liquid. So in case of a fluid, the moment you apply shear stress, the liquid or the fluid will start to show strain. Strain is deformation. So what will happen is, since the strain will continuously go on increasing, it is quite impractical to relate stress with strain, because in a solid you apply a stress, you generate a fixed amount of strain, and then you can show through experiments that they have some relationship between each other. In case of fluid, instead of stress strain, what happens is stress is related to the rate of strain. Okay, we will talk about what is this rate of strain. So if you okay, let me just complete this description for the moment. So in fluids, okay, in solids, stress. So in a solid, you would see a stress versus strain plot. Okay, sometimes you can have a linear plot. Sometimes it can become off linear, which is non-linear, off linear. not linear in some regimes of the stress strain domain. In case of fluids, you will see that shear stress is related to the rate of strain, not strain, but rate of strain, d theta dt, and we will say what is really this thing. So you can think of theta, say, you start with, okay, let's just go back to this particular diagram. This is something that is commonly dealt with in the discussion of kinematics of fluids. So you start with a certain angle. Okay, here it's angle is, you can have an angle theta, and what is happening is, you see there are some velocity gradients at play. Okay, so this is a chunk of fluid ABC, chunk of fluid ABC, and we are choosing two directions that are orthogonal to each other. So AB is normal to AC, and we are saying, okay, this angle, let it be K. I think let's just call it K. Doesn't really matter. So we don't need to invoke Greek letters all the time. So let this angle be K, or let this angle be theta. Okay. Now what happens is, as the flow is moving at a time, so this is the fluid element at time t, and this is the same fluid element at time t plus delta t. Now see, what has happened is, this element has deformed. Okay, so remember, strain has something to do with deformation divided by the initial, scales. Now, in case of a fluid element, you see that the deformation is a little different from the deformation of solids. And in this case, the deformation is given by the summation of del theta 1, del theta 2. You see that if this point has a velocity of u, in the same spirit as we have done, several times other problems, and the x component of this is u plus the rate at which u is changing in this direction multiplied by the extent in which the change actually happens. So if the velocity x component of velocity of A is u, then the x component of velocity at B is u plus dou u dou y into dy. So then what is the relative displacement between A and B? So when A has moved from here to here, B has moved from here to a little bit more, because you see it has some extra terms. So the relative shift in the x direction is given by the relative velocity into the time. So this was the difference in the velocity in the x directions. So this was u, and this was u plus something. So the difference in x velocity between A and B was dou u dou y times dy. So the relative displacement in the x direction of this point B with respect to A will be this thing. Similarly, if the v component of velocity of A, the y component of velocity at location A was v, and we give the liberty, or the flow field is such that the v is also changing with respect to x in this particular case. So then v becomes v plus the rate of change of v with x multiplied by the extent through which we go from A to C. So then your point A is moving in the y direction at a velocity of v. Your point C is moving at a velocity of v plus dou v by dou x into dx. Then at the end of this duration delta t, your point C would have shifted by an amount this with respect to the point A in the y direction. So point B is shifting in the x direction with respect to point A, and point C is shifting in the y direction with respect to point A. So what is now my, these angles, delta theta 1 and delta theta 2? It is nothing but, if you think of the tan theta relationship, opposite side by adjacent side. So opposite side is given by this expression, this one and this one, opposite side. Adjacent sides, so here we are saying that my v component of velocity changes only with x direction, and here we are saying u component changes only with y direction. It could be such that your v is also changing with respect to y, v is also changing, u is also changing with respect to x. That is also possible. Something similar comes out of it. So Then what is this delta theta 1? It is opposite side by adjacent side, because remember your tan theta for small thetas become theta. So then delta theta 1 is this thing, delta theta 2 is this thing. This thing is just nothing but opposite side by adjacent side. So opposite side is dou u dou y into dy into delta t. Adjacent side is dy, okay, because in this particular problem we are, and if even if you have the changes in v in the y direction and changes in u in the x direction, you can work out an order of magnitude thing and neglect them even. So we have delta theta 1, delta theta 2, and then the rate of, so this is the strain rate. Okay, so strain rate is given by, so you see the delta theta 1 by delta t plus delta theta 2 divided by delta t. So this is gives you the rate at which this angle is shrinking or changing. So that is the strain rate. In some cases you also have a dot on top of it, but you can just stay with this convention. Now, so now from the basic stress strain, the way we say is you have the strain rate in this particular xy plane. In a Newtonian sense, this strain rate would be linearly related to the stress causing it. I mean, this is observed in most fluids. Okay, so that class of fluid is known as the Newtonian fluid. So in Newtonian fluids, your stress in the xy plane, or rather the tau xy or tau yx, we will show the equivalence of them maybe in the next slide. So this is related to the strain rate, and if it is linearly related like that, then we say that this is a Newtonian fluid. Or in Newtonian fluids, these strain rate is related to stress in a linear fashion. So if you remember, so at this point you know how to get the strain rate. So you can start with, this is a common description of fluid kinematics in a lot of textbooks. So if you, in Anderson's book, it's there in many textbooks, it is there. So look for fluid kinematics, chapter on fluid kinematics. And this gives you the rate of deformation, which is nothing but the strain rate. Okay, so in fluid kinematics, this is the way we show the rate of strain of a fluid element, and then stress is related to the rate of strain of the fluid element, and if it is a Newtonian fluid, then it will be linearly related to the the strain rate. So in fact, if you remember this slide that I showed a moment back, so this is my shear stress and this is my strain rate. So here I'm using d theta dt. It doesn't matter. You essentially that angle. So you start with the right angle between the two fluid axes, or rather you think of you draw a right angle and then you see how the fluid, how that angle changes as the fluid convex or moves from well, don't you want to say convex or anything, like as the fluid is, you observe the fluid over 2 instances of time, okay, delta t later. So you see that the Newtonian is where your stress strain rate relationship is linear. Okay, it's a straight line. So that is the y is equal to mx, and you can see that it's going through the center. So it's like y is equal to mx plus c, where c is 0. On the other hand, you can have situations where the behavior is such that initially you have behavior like this. So at some levels of shear stress, a small change in shear stress creates a large change in the strain rate. So that is given the special name pseudoplastic. So essentially this is Newtonian, the red line. Everything other than that Newtonian will be non-Newtonian. So that's the broad classification of this other. So this blue, for example, is non-Newtonian, and given the specific nature of the stress strain rate variation, that is at a certain level of shear stress here. See, when you increase shear stress from here to here, you actually have a very large variation in strain rate from here all the way to here. Okay, so a small variation in shear stress at a high level of shear causes a large change in the strain rate. Okay, so that is your pseudoplastic. On the other hand, your you have, so this is called a dilatant. So what happens is at high levels of shear stress, a small change in strain rate causes a large change in shear stress. Then you have the plastic behavior. Then you have ideal Bingham plastic, which is it actually there is no strain rate till you apply a certain amount of shear stress. So you're applying a shear stress, nothing is happening. You're increasing the shear stress, nothing is happening. You're increasing it even more, nothing is happening. Then all of a sudden, at a certain level of shear stress, you see some strain rate is starting to happen or show up. Okay, so here, so this is okay. So this one is for your parallel flow, where you have variation in velocity only in one direction. But again, I must emphasize that this is the more generic form. Okay, so you include the variation in those two directions. But of course, if it is a planar flow that nothing is changing in the other direction, then you can just use. Okay, so this is actually the generic expression. This thing is yet to be proved, why those subscripts can be interchanged. This particular form is true for parallel flows, but for most cases, I think you should start with this and then justify if it is a parallel flow or not. This mu is known by the name dynamic viscosity, and sometimes mu by rho, which is the density, is given the name kinematic viscosity. Okay, to emphasize once again, in solids, stress is related to strain, and that can be linearly related, non-linearly related. Maybe initially it is linear, then it is non-linear. In fluids, on the other hand, this is a very important distinction. So if someone asks you what is this difference between solid and fluids, of course this may not be the first answer you should give. There are other definitions or differences between solids and fluids, but this is also one of them, that stress is now related to strain rate. Okay, so again, if it is non-deforming, then we are looking at pure normal stress or hydrostatic state, because the moment you apply something that is not normal stress, essentially the moment you are applying shear stresses, the fluid will start deforming. Once again, since the fluid will continuously deform, it is meaningless to talk about the relationship between stress and strain. But we will see that stress is related to the rate of strain. For Newtonian fluids, the relationship is linear, but there are non-Newtonian behavior of various kinds. The ideal Bingham plastic, for example, is something that it starts responding only at a sufficient high level of shear stress, and then it has in this graph here, it almost looks like a linear relationship, but it has that initial threshold that has to be crossed. Now, a little bit of discussion on what is the shear force or shear stress, because this thing will be very important. You already saw its importance when we were looking at the shear stress or the skin friction drag, etc. But again, because we will be looking into the boundary layer phenomena and things like that, it is important to at least see the nature of the shear stress. So it's a classic problem where you have a plate. So essentially there are two plates and there's fluid in between, and the height between the two plates is h, and you are pulling the top plate at a force F. Okay, so if the F by A is nothing but the shear force, okay, force per unit area, and you are pulling it with a velocity v. Now, when you start pulling it, I think some transients will be there, but eventually, what will happen is you will end up with a situation where so if you impose the condition that the shear stress is constant along this height, what will happen? And part of the reason is, since the pressure outside these parallel plates is same, this is a flow driven by shear forces only. And if you go from cross section to cross section in experiments, for example, you will see that the profile doesn't change. So the profile has actually a very interesting feature, which I will talk about soon. The profile doesn't change from location to location. So essentially, then the forces that are acting on the fluid element is zero. So there is no pressure difference acting on this fluid element. There is some shear force that is acting because, see, the flow in touch with this lower plate, stationary plate, is not moving at all. Flow that is in touch with this top plate moving to the right with the velocity of v is also moving to the right with the velocity of v. So there is a velocity gradient. Okay, so we don't know exactly what kind of velocity gradient, but at least we can say that since the cross-sectional profiles look similar once things have settled, there is no acceleration from the as you move along the x direction. So then there is no net force on this blob of fluid. So you can say that maybe that although the shear forces are acting, they're acting, of course, they're acting in opposite directions, because remember from that elemental volume argument, that is the layer below this lower layer is slower, layer above this upper layer is faster. So the layer above this layer will tug this top layer to the right. So that's why you have this. So this shear force is acting on the right hand side because the layer of fluid above the top layer of this small chunk of chunk of fluid element is pulling it to the right, whereas for this surface the shear force is directed to the left, because see here the velocity is 0, here the velocity is v. So there is some increase of velocity in the y direction. So this is pretty much, if you have followed how we set up the direction of the shear forces on that small parcel of fluid, the free body diagram, then I think you will appreciate this thing already. So now, since there is no acceleration, so this tau is equal to this tau, and there is no pressure difference, so these taus have to balance each other because there is no acceleration. Because if you go from station to station, the flow looks the same. So then tau is constant. It's a parallel flow problem. So we say mu times du dy is equal to constant. Parallel flow problem. V and other components are not well. At least we are looking at. So in this problem, we are using u in. So u is this one. So u is still the x direction velocity, but it has variation in the y direction. Okay. In fact, we will see that u actually varies linearly like this. So this is what falls out of this thing. So when we say the shear stress is constant, because there is no pressure force acting on, well, no net force due to pressure difference acting on that element. Pressure forces are acting, of course, but there is no net force in the x direction due to pressure difference or anything. So, and there is no acceleration of this fluid chunk. So then the shear forces balance each other. So the shear forces is constant. So mu times du dy is constant. Then by differentiating this, we can say the second derivative of u is 0. If you now integrate this thing, you will see that uy becomes a function of v by h times y. So that's a linear variation in u. So just like a constant tau will give a linear variation in u, similarly a linear variation in u will give you a constant tau. So again, this is a parallel flow problem. So this is a classic problem, and the effect of viscosity is demonstrated by this problem. Okay, so that is a viscous fluid between two parallel plates. The top plate starts tugging along. Well, the top layer of liquid flows, because of the no slip condition, cohesion, and other things. The top surface moves with the velocity of the plate, and this top layer of fluid actually keeps on pulling the lower layers from left to right, and eventually you have a profile given by this constant velocity. Okay, so we are yet to prove this particular aspect. tau xy, tau yx, and then once we do it in the next class, we will get into some discussion on some of these other aspects of viscosity, and then eventually move into our energy equation. Once we are done with energy equation, we will go into Reynolds transport theorem and see some analogies. We'll spend a little bit of time in like CFD understanding, these partial differential equations, how they're useful in the numerical schemes, and then we will get into some other aspects of this problem of aerodynamics, not of this one. Okay, so thank you for your time, and I'll see you in the next class.